Hello everyone, welcome to lecture 1, sets and subset. In this lecture, I'm going to break it down into multiple short videos for easier watching, so you can learn the material step by step without feeling overwhelmed. So in this video, I will introduce the basic language of discrete mathematics by exploring the concept of set notations, and cardinality, which is the sign of a set. And we will also look at the finite and infinite set and also the concept of empty sets. So the first thing we're going to explore is look at the definitions of a set. So a set is an unordered collection of distinct objects. So in this case, an object can be defined as the element of the set. The elements can be numbers, strings, tuples of numbers, and can even be other sets. Before we go into an example of describing a set, we need some notations to describe a set. So one way to describe a set is use something called set roster notation. So for this notation, what you do is that you explicitly write down the elements. Now to describe a set, what you do is you have the capital letter indicate the set that you're working with, the equal sign, and the elements that you're going to explicitly write down will be included between the two curly brackets. So in this case, the set S consists of the following components or the following elements. Let's say the set S consists of 1, 3, 5, 7, 9. So the set S is written as follows. Capital letter, equal sign, two curly brackets, and the element that you want to explicitly write down. In this case, you have 1, 3, 5, 7, and 9. So this is the set of numbers. You can have the set of strings. In this case, I have the set of apple, banana, avocado, and you close the set with another close curly brackets. Or you can have a set consists of all the sets. In this case, let me introduce the set W. This is the set consists of set S and the set F. To describe an element inside a set, you're going to use the following notations. So this looks like a letter E, but it's a little bit curvy here, and then the line in the middle. So in this case, I want to say that the element 1 is the element of the set S. So I'm going to write 1 is an element of the set S. Now I can also say that apple, the string apple, is an element of the set F. So again, in this case, this notation is element of. On the other hand, a notation to describe something that does not belong to a set. So still we're going to use this notation, but then we put a line through it. This set right here is saying that not element of. So in this case, I can say that number 2 is not an element of the set S. Now, in addition to the set roster notations, you have another notation to help you describe a set. It's called a set builder notation. So set builder notation is used to describe sets precisely and compactly using rules instead of listing every element. So the general form of this set builder notation is given as. You also use the notations of curly bracket, but within the curly bracket, now you have X. This can be expressed as a variable or the representative element, and a small vertical line. This particular notation means such that, and then you can write down the conditions of X. So let me explain this a little bit. So the vertical line you see inside the set is called such that. X in this case is a variable or a representative element. For example, we want to use a set builder notations to describe the set of all number X such that X is greater than 0. So the statement that we have is that the set of all number X such that x is greater than 0. So now we're going to use the set builder notations to describe this statement. The statement is equivalent to the set of x such that, with the vertical line, x is greater than 0. Let me move this in a little bit. Now let's try another example. I want to describe a set of all even numbers. To describe this statement, I'm going to use two different notations. The first notation is the set roster notation, and the second notation is the set builder notations. For the set roster notations, I'm going to use this curly bracket, and I list out the element of the set, including 0, 2, 4, 6 on the positive side. And you can go on to positive infinity, or you can go to negative infinity side, and you have -2, -4, and -6. Because there's infinitely many even numbers, that's why when we describe this type of problem using the set roster notation, what you do is that you use ... to indicate that there are many more numbers or elements beside what you describe here. So here I want to describe -4, -2, 0, 2, 4. Then I use comma, ... and I close the set. So again, there's infinitely many even numbers. I just try to write down some representatives of the even numbers. Now, the set builder notation is going to be very helpful in this kind of problem that you are dealing with infinite sets. And you can use the set builder as follow. You want to include all the value of x such that x is equal to 2 times the integer. And you close the set using the curly brackets. So in this case, this particular statement or this particular notations already help you to describe the set of all even numbers. That is, you want to describe all number x such that x is equal to 2 times the integer. So integers, we're going to explore that a little bit later, but the integer including the number such as 1, 2, 3, 4, that's the positive integer. You can include 0, you can include negative integer as well, such as -1, -2, -3. Now we can do the same thing for the case of odd number. You want to also use two different ways to describe this set of all odd numbers. For the case of set roster notation, you can write down a few representative of odd numbers, including -3, -1, 1, 3, so on and so forth. And in terms of the set builder notation, you want to include all the value of x such that x is equal to 2 times the integer plus 1. So this type of conditions for x inside the set builder notation is extremely helpful for you as the computer science major, because it's help you to write down the code a little bit easier. So instead of listing out a lot of numbers, you can just write down a formula and then help you minimize the number of lines of code that you have to write. Now you have heard me mention about infinite sets. What is infinite set and what is the finite set? And how would you define if a set is a finite set or if a set is an infinite set? To identify a set to be finite or infinite, what you do is that you need to calculate the cardinality of a set, which is the next topic that we're going to explore. So the cardinality of a set is the number of elements in a set S. Number of elements in a set S. The notation for this is going to be that. So it's look like an absolute value, but in this context is indicate that you want to measure the number of elements inside a set. It's called the cardinality of a set. So for instance, I have a set of S equal to 1, 4, 9, 16, 25. Because there are 5 elements inside the set, I say that the cardinality or the psi of S is going to be equal to 5. Now I have another set, let's say the set A, and the set A including apple, banana, and avocado. And because there are 3 different elements inside this set, I say that the cardinality of the set A is equal to 3. Now I have some remarks for you in terms of defining the finite set in infinite sets. So if the set S has only finitely many numbers, then the cardinality is a finite number. And with that, S is defined to be a finite set. If the set S has only finitely many numbers, then the cardinality of S is a finite number. This implies that S is a finite set. And in many cases, the psi of S could be infinite, in which case the set is called an infinite set. There are many infinite sets that you are dealing with in mathematics and computer science and physics, including the set of all natural numbers, the set of all integers number, and the set of all rational numbers, and the set of all real numbers. So for instance, here you have the set of all natural numbers is described using this particular notation. So this is capital N, but with the line like this. So this is the special notation to indicate that you are working with natural number set, or the set of all natural numbers. And this is equal to 1, 2, 3, 4, 5, so on and so forth. For the set of all integers, you have this notation z, and with a line like this. So this is the set of all integers. This including -3, -2, -1, 0, 1, 2, 3, so on and so forth. Or you can have the set of rational numbers, and this notation like that is the fancy Q to indicate that this is the set of all rational numbers. So it's a lot easier for us to write down the set of all rational numbers in terms of the set builder notations. That is, this is equal to the set of all the fractions P over Q, such that P is an integer. So in this case, P is an element of the integer set, and Q is also an element of the set of integers. And one more condition for Q is that Q is different from 0. Because this is a fractions, you don't want 0 in the denominator. And one last notation I want to give here is the set of all real numbers. This is the fancy R, indicate that you are working with the set of all real numbers. So the set R consists of natural numbers, integers, rational numbers, irrational numbers, set h pi, square root of 2, square root of 5, number e, so on and so forth. Now you have a finite set, you have an infinite set. Now what about empty set? So the set that contains no element is called an empty set. Sometimes the empty set is also called a null set. The notation for this is that this is written as just the curly bracket like this, spacing out a little bit, or we can use the notations of the letter O with the line through it. These two notations are used interchangeably to describe an empty set. Next, I'm going to give you a few remarks about the order of the elements, the equality of two sets, and repeated elements inside a set. So the first remark is that the order of the elements in the set does not really matter. You have seen a few examples that we write down the elements inside the set in certain order. That's because in conventions, when you work with real lines, you work with number lines, everything has to go from negative infinity to positive infinity in that particular order. But in terms of discrete mathematics, when you put things into a set, it doesn't have to follow in any particular order. That is, you can have the set be 1, 3, 5, and you have another set to be 3, 5, 1. And these two sets are considered to be the same. In addition to the first remark, two sets are equal if and only if they have the same elements. Just as you see here in this example. Now, it does not matter if an element of a set is listed more than once. That is, you have a set A. This is equal to apple, banana, and avocado. In the set B, I have the set consists of apple, banana, then another apple, avocado, and another apple. So as you can see, the string apple appeared 3 times. However, in this case, the set A and the set B are considered to be the same. The repeated elements are ignored. So it's like when you consider this type of set, you consider the type of elements that you have inside the set. In the set B, you have 3 different types of fruits: apple, banana, and avocado, not the number of apples that you see in the set B. Similarly, in set A, the type of fruits that you have inside set A is apple, banana, and avocado. And because we have 3 different types of fruits in set A and 3 different types of fruit in set B, set A and set B are considered to be the same. And that's it for the first video. Now we're going to move on to the second video. In the second video, I will talk about subsets and proper subsets.